So here we have a hypothesis that, again, has been suggested by some NASA scientists that these things here, these objects here, represent microbe fossils that were actually deposited on Mars, and therefore would imply that there was, at least in the past, life on Mars. So let's think about this for a moment, though. Just because the objects look like microbes, is there any other explanation? Are there any other explanations that could explain what these things are that don't involve life? In other words, could these things just look like microbes but are actually something otherwise natural, some sort of geological phenomenon? That is what we mean, the Bologna detection kit, of considering alternative hypotheses. What else could explain what it is that we're looking at? Now, there's more that you need here, though, too. You've made the hypothesis. To test the hypothesis, this is what we're doing. We're sort of asking what other possibilities are there. But that alone is confusing. If we're questioning whether or not this statement is correct, does that mean that the statement must be false? This is a very, very common fallacy in people's arguments. So here's the statement. Because alternative explanations exist, does that mean that they're not Martian microbes? A lot of people seem to think yes. Just because there's another possible explanation that could explain what's going on here that's not alive, that means that they can't be alive. Now that statement doesn't make sense. Just because there's another alternative, all it means is we don't know. It doesn't mean that what they think, what NASA might suggest, is wrong. It just means we don't know if it's right. That's a difference. There's a big difference there. Just simply saying that there are alternatives is not negating the original statement. So we have to think of it as we have to test all of those ideas. It isn't just that saying something else could exist actually tests the idea. It doesn't. It doesn't test it at all. That's not even part of the test. It's just something else we have to test now. So here's the question then. What other evidence could exist here that might support these being Martian microbes? I'm going to leave that open to you. I want you to think that through. I want you to think about that. Now here you can go to the internet if you want and study the situation. Find other people who've made suggestions. Think about it yourself. Come up with your own suggestions. Post that to the discussion board and we'll discuss it. We'll see what goes on. If you come up with good ideas and you come up with a solid discussion and you make contributions to that discussion, there may be a couple extra credit points I'll put on the next exam for you. But I want you to think it through. And the reason I want you to think it through is not just because this is an interesting problem. You may not find it an interesting problem. I don't know, I do. But because it's the thought process that's what's important. That's how we have to think about this. Okay, so that's how we approach hypotheses. We test them, we think about them, we look at alternative hypotheses, we try to figure out what other evidence we need to test it further. That's how we deal with it. But the question then arises, how is that concept of hypothesis related to the concept of theory? Now, like I said before, a lot of people see theory and hypothesis as the same thing, as the same idea. They say things like, well, that's just a theory, implying that we don't know what's going on. It's precisely not how scientists use that term, however. So here are a couple of things. And again, I don't want you to just take it from me. I want you to see from other situations how people see things. And this series of questions comes from a book written by a biologist named Eugenie Scott. And she was asking these questions: true or false? Theory and hypothesis mean the same thing. Or theories are highly speculative. Or if a hypothesis is tested and passes the test, it becomes a theory. Or if it passes further tests, it becomes natural law. The goal of science is to produce theory. That's my addition to this whole set of questions. Now, I'm not sure how you would answer them, but I want you to try. Think about what that would mean. Let's start with this one. Theory and hypothesis mean the same thing. Well, if you've been listening to what I've been talking about, you should know, yeah, they don't. I'm saying that they don't. But to many people, they do. Like I say, they really do. So we can't just negate that and say that's not true. We just have to be clear what we mean when we use the word theory. Okay, true or false? Theories are highly speculative. Again, most people that I've spoken to who are not scientists would tend to say yes. If a hypothesis is tested and passes the test, it becomes a theory. If it passes further tests, it becomes a natural law. This is what I was taught in elementary school and junior high. That was the concept. I'm not actually sure. I haven't sort of dug back in time to determine how these things are related and where that idea came from. But again, people who have studied at least in certain areas would say, yeah, that's true because that's what I was taught. And the goal of science is to produce theory. Now, I ask people this all the time. The goal of science is to produce theory. Almost always they say no. That's obviously not what it is. Now, here is what the consensus appears to be among scientists. Scientists would generally say that theory and hypothesis are not the same thing. They generally say that theories are not speculative, meaning it's not a guess. It's exactly the opposite of a guess. And also, we don't tend to think of hypothesis being tested and passing a test becomes a theory. A theory is not a tested hypothesis, not in the way we use that term. A theory is something different, and a natural law is something different. One of the reasons is this: a hypothesis is kind of an explanation, and a theory is also kind of an explanation. We'll see that in a moment. But a natural law is not. A natural law is simply a statement of the way things are. So, one of the natural laws being that there's an acceleration constant for mass in the universe. Why is the number of the acceleration constant what it is? We don't know. We don't really have an explanation for it. But what we do know, though, is that it's something that has been tested over and over again. We know it's true. We just don't know why. So we call it a law. But look at this. The goal of science is to produce theory. That is our goal. That's what we are producing. What then is theory? If this is our main product, if this is what it is that scientists are producing, then what is it? Well, it's a fairly difficult thing to explain, except if you're a scientist. I think that's one of the reasons why people use that term so loosely, and also because in law, for example, the concept of theory is like a hypothesis. They talk about the theory of the crime, which is a statement of how they believe the crime occurred and so forth. So here, though, is the concept of theory from a scientist. And in fact, these two scientists, Gerald Holton and Stephen Brush, are physicists and historians of science that were from Harvard, and they wrote one of the most beautiful textbooks I've ever read. It was a non-majors textbook, an old one now, for physics. And in that book, they were talking about what is theory. And they say specifically, a theory is a conceptual scheme that explains to ourselves and to others observed phenomena. Let's stop there. Okay, let's think about this for a moment. What is a conceptual scheme? What is that? Well, a scheme. What's a scheme? You've heard of people scheming, I'm going to scheme and do this. Well, a scheme is a plan. That's all it is. It sometimes has this negative connotation, but it doesn't have to be. For example, blueprints are often called schemes. So a scheme is simply a plan, a sort of a layout of the way things are related. And of course, conceptual means ideas. So this is a layout, a blueprint, if you will, of ideas that explains, and that's the key phrase, it explains to ourselves and others observed phenomena, not supernatural phenomena. We're not trying to deal with that in science. Whatever supernatural phenomena may or may not exist, we can argue about it. I'm not going to argue about it because it's not part of what science is all about. Science is looking at the natural world, so we're looking at observed phenomena and relationships among them. That's the other key word, relationships. It brings into one conceptual structure the laws, concepts, principles, hypotheses, and observations, often from very widely different fields. Okay, that is a theory. On a simple level, a theory helps us interpret the unknown in terms of the known. So let's go back to that example I was talking about before. You're working as the attending physician in an ER, in a trauma center. And somebody comes in and they're unconscious and you don't know why, and there's no obvious explanation based on what you see on their body. What do? You consult theory. You consult the theory that you were taught in medical school, the theory that you were taught after you left medical school, the theory that you learned as a practicing physician. That theory is what you know. That is what you understand. And that is what you consult to determine what is going on with this patient. That's what we mean. So if we do something like send a spacecraft to Mars, or like the Voyager spacecraft, we send it out of the solar system, we consult theory. When we try to explain why it is that a particular disease is spreading through a society like COVID-19 did, we consult theory. We try to figure out what's the best way to contain a disease like COVID-19. We consult theory because it's what we know. Now, you might read that Holden Brush statement and still be confused, as honestly I was the first time I saw it. There's a lot there. There's a lot to be thought through. Now, the National Academy of Sciences, however, states essentially the same idea, not quite as deep, not quite as expansive, but a little bit more clear. And their statement from the National Academy of Sciences, again, this is the body of scientists that is understood, at least in the United States, to be the leading scientists of the country. And what they state is the definition of theory is a well-substantiated explanation. Notice, well-substantiated. Again, exactly the opposite of a guess. Something's well-substantiated is something that has a lot of evidence supporting it. So much evidence that we use it as a, not a belief, but we use it as our operating understanding of the universe. So it's a well-substantiated explanation of some natural aspect of the world that can incorporate facts, natural laws, inferences, and tested hypotheses. So you see the parallel. It's an explanation, and it is about the natural world, observed phenomena. Again, we're not asking questions about a supernatural phenomenon. We're asking only questions about things that exist in the natural world, which is absolutely critical. We have to keep that in mind. The scope of science, the realm of science, is only the natural world. That's it. And again, you can see again, it has the same idea of incorporating the facts, the laws, the inferences, and the tested hypotheses into one structure. One of my favorite expressions of this came from J. Robert Oppenheimer. Now, Oppenheimer was the chief scientist, the head of the Manhattan Project during the Second World War that made the first atomic bombs. He later then worked in the Nuclear Energy Commission and worked actually very strongly to try to keep the bomb from developing. But he was a brilliant theoretical physicist, and he had a beautiful way of expressing things. He had a beautiful view of science as it was. Now, late in his life, as he was dying of cancer, because of course all these guys were exposed to radiation, they didn't know how dangerous it was at that time, while he's dying from cancer, he gets invited to give a series of 5 lectures. And the 5th lecture is one that you really should read. It's gorgeous. It talks about science as a house, the house of science. Now, I'm going to use some paraphrasing here of the way he expressed it. I'm going to express it more generally. He was talking about the house of physics. I'm talking about science in general. Same idea. Here's what a theory is. A theory is the house, the structure, that which we call what we know. And it's where we as professionals live. We literally go into that house and we build pieces of it. We redesign, we remodel parts of it on the inside as more information comes in. We build wings and expansions on it as we develop new parts of the theory. But the theory itself, just because we redesign a room, we don't say that the house ceases to exist and needs to be torn down. We simply change it. We make it better. It isn't that the room was wrong, it just wasn't complete. And the same thing with the house. The house doesn't need to be torn down every time you want to add an expansion. You simply take what you already know to be true and you add to it. So one of the things that you'll hear is that somebody will come up and say, oh, they discovered this new thing that has completely changed our understanding of science. Ladies and gentlemen, that has never happened in my lifetime, not once. It just never has. That's hype. Don't get confused. What they've done can be fantastic. It can be Nobel Prize winning work, but it doesn't tear down. It builds. It adds to what we already know. So our idea of science doesn't change like that. It's always an addition. It doesn't say we don't make mistakes. We do. But when we do, we fix it. We go in and remodel the room, make it better. But we don't have to tear the house down in order to do that. That's the key point. So that's the point. Our goal of science is to produce theory. And theory is connecting things with an explanatory framework and all the different things that we know and all the evidence information that we have into something that explains what's happening in the universe. That's what it is. Okay? That's what we're trying to do. Perfect theory would explain all of nature in the simplest possible way. Is that possible? Is that even a goal? Who knows? I don't, that's way beyond where we are right now. But the point is that we do have a number of very, very successful theories. And when I say successful theories, I mean they are used over and over and over again to get the correct answer. For example, theory of universal gravitation. That's a theory, and yet we use it every single time we send a spacecraft into space. And every single time that we fail, it's not because of the universal gravitation theory. It's because somebody didn't convert metric into English properly in some of the engineering. It's never been a failure of universal gravitation. Theory of plate tectonics explains why it is that we get earthquakes where we do, why the mountain ranges exist where they are, why some are still growing and some are declining. All of that has been extremely successful. Theory of natural selection explains why there's so much diversity. It explains why it is that whenever we treat cancer, in certain situations, it comes back, and when it comes back, we can no longer treat it. That comes from the theory of natural selection. Theory of relativity, and in fact quantum theories in particular, are the most successful theories in all of science. Quantum theories have never failed a test, not one. They're absolutely bulletproof. But they're completely counterintuitive, which goes back to the theme that I was talking about earlier. Don't confuse your intuition with logic. Logic comes from mathematics, not from what you think makes sense. That's a very, very different concept. All right, so that is an introduction to how it is that scientists think. This is not something that we take as dogma in the way we have to be. It's something that we're using because in the past it's been extremely successful. It's allowed us to make 747s that fly. It's allowed us to, as I mentioned before, increase the lifespan of people throughout the world. It's allowed us to live largely disease-free lives. It's allowed us to develop technologies that are on the cusp of allowing us to do DNA surgery, molecular surgery. We're going to talk about that later in the course. All of that comes from this way of thinking. So we value it very, very highly. That's why. So here's a question then. Here is, going back to Lowell's theory, here's a piece of Lowell's theory of Mars. Okay, now, you can call this his theory, just that picture right there. Now, was his theory wrong? Well, yeah, there's no civilization, there's no canals. Yeah, but it wasn't entirely wrong. What's this white stuff, right? Well, he thought it was water ice. Turns out he was wrong, it's mostly CO2. But we now know that there is water at the poles, both poles. I'll give you the evidence for that later. But the point is that even though Lowell was wrong, much of his theory was wrong, we don't discard the whole thing. We certainly don't say Mars doesn't exist. And this is something that sounds really stupid, but actually I want you to go watch any political argument, and you'll see a lot of this sort of argument over and over again. Well, this one thing that you're saying was wrong. You've said 10 things, but one thing was wrong, therefore we're going to throw all 10 things out. No. That's like saying, okay, one thing Lowell was talking about was wrong. There's no civilization. That doesn't mean Mars doesn't exist. Doesn't mean Mars isn't red, and so on. So the point is we can't throw everything out. We take what's right and we keep it and we revise the rest. How do we do it? With evidence. Here's the evidence we had that I showed you earlier. This is the picture coming from Mars Reconnaissance Orbiter that has looked at this planet to a resolution of 1 to 2 feet. And we now know there's a huge canyon right here. And that canyon is, when I say huge, I mean huge. See this end right there? Compare that to this end right here. The distance from here to here is the same as the distance between Los Angeles and New York. So it's a canyon the size of North America. So this is our modern theory of Mars, but it's not complete. We know, for example, that this is CO2. How? We didn't guess. We didn't say it must be that. We found out from evidence from the orbiters and from the landers that we had. Actually, there's one up here that's called Mars Phoenix, which replaced Mars Polar Lander, which actually turned into Mars Polar Crasher. But that actually demonstrated there is water ice, but there's also CO2 up here. And that's mostly, the white that you see is mostly dry ice, CO2. But we also have more to our theory because we have these other things. We went up with magnetometers, which can measure the gravitational field of the entire planet. And here is a gravitational map of Mars. The blue areas have a low gravity and the red areas have a high gravity. And you see right here, this really, really dense area of high gravity. That's a big volcano and so forth. So this is also part of our theory of Mars. So why is it that our theory of Mars is correct and Lowell's is not? Well, that statement itself is not correct. Lowell's theory was in part correct. It was maybe mostly wrong, I suppose, depending on how you look at it, but he was right about a few things. One of the things he was right about, most astonishingly, was that in fact Mars did have lakes and rivers and streams and oceans in the past, and there was an ecological disaster. How do we know that? I'll show you the evidence for that in a little bit. But he was right about that. He was right maybe for the wrong reason. But that's the point. The point is he wasn't wrong. But now the question is, why is our theory superior? It's not hard to see based on what I'm showing you. There's no way Lowell could have gotten this gravitational map of Mars. He didn't have the instrumentation. So why is our theory better? It's not that we're smarter than he was. He was a brilliant, brilliant scientist himself. It's that we have better information. We have better technology. We have better ways of looking at things. We have much more powerful telescopes. We have landers that can land on the surface of the planet that he didn't have. So it isn't that he was stupid. Don't get the idea that people in the past, especially the ancient Greeks, when you look at the stuff that they did, and you look at not just the mathematics, but the engineering, it's phenomenal. It's phenomenal stuff. They're not dumb. Our theory is not better because we're smarter. Our theory is better because we have better information. And our technology has improved. So we have to have a lot of respect for the people that come before, and we have to listen to them, which is why we don't throw theories out just willy-nilly because we think the people in the past got it all wrong. If we do that, then we'll get it wrong. We have to be smart. And that is ultimately what science is. Science is being as smart as you possibly can all the time. Science is nothing more, the scientific method is nothing more than being relentlessly intelligent. Be as smart as you can all the time. Now, it's hard to do. It's very difficult to do. And it happens that we make mistakes. It happens that we're not as smart as we should be at times. But in our profession, that is our goal, to be relentlessly intelligent. And that's the key to it. So that ends this module. Now, after you've done all the aspects of that module, it is time for you to take the quiz. Make sure before you do that, though, to look at that study guide, go through all the questions in the study guide, and answer them out as if you're answering them on a test, and then take the quiz. If you do it that way, it'll go much, much faster, and you'll learn a lot more deeply what's going on.